Hello, and welcome to the Math Magic Show. In this one, we're going to take a look at finding the following using a Riemann sum, so the hardcore math way. I'm going to integrate between 0 and 1, x squared dx. So before I get to that, I need to first draw a picture so we can motivate each part of the Riemann sum. That will make it much more meaningful for us. So imagine this situation. Imagine this is our vertical axis, our horizontal. I'm integrating from 0 to 1. So imagine this is 1 over here. This is x and this is y. The function is x squared, that's our integrand. So that kind of looks like this. And here, let's draw in some rectangles because that will help us to decide on building up the sum correctly. So as an example, imagine that the rectangle looks like this, and there's another one that looks like this, another one that looks like this, another one that looks like this. Okay, the dot dot dot, that means there's some other rectangles in there I'm not showing you. And then maybe at the end you have one more rectangle that looks like that, for example. So we want to know this for the following reason, because what it tells us, first of all, since the whole portion right here is equal to 1 unit, each base of each rectangle is 1 over n, because you're dividing it by n. So for example, if you have 50 rectangles, each base would be 1/50th. If you had 100 rectangles, each rectangle, the base would be 1/100th, and so on. So in general, you don't know the value of n, so you just say that each one is 1 over n. That's the width right here, that's 1 over n. That 1 over n also becomes our measuring unit. So what do I mean by that mysterious statement? What I mean is, say this is the first 1 over n. Then after that, this is 2 times 1 over n. It's twice 1 over n. Then this is 3 times 1 over n. Then this is 4 times 1 over n. Then you go all the way to the end. So what happens over here? That's a good question always. What happens at the 1 itself? You can express that in terms of n by saying that this is equal to n times 1 over n. In simple English, what it means as an example is this. Think about it. For example, if n has the value 100, then that's like saying 100 times 100th, which would be 1. If n has the value 1000, it would be like saying 1000 times 1/1000th, which again would be equal to 1. Now when you look through this, the first one is really 1 times 1 over n. Also don't forget that. There's something important. Let me delete this little piece over here. We don't need that, so it's out of the way. And what I mean by that is this. Take a look at this number. That's 1, that's 2, that's 3, that's 4, right? It goes all the way up to n. So it goes from 1 to n. That's the changing quantity. So based on that, you can get the values of x. So what I mean is the general value of x will look like this, would be k. Now the k that I'm writing here represents the 1, the 2, the 3, the 4, and in turn all the way up to 1. You see that? That's why the k is needed. Then you would multiply by 1 over n. The 1 over n is just, as you can see, the width of the first little rectangle right here. And then when you do 2 times k over n is twice that. When you do 3 times 1 over n, then it's 3 times. When you do 4 times 1 over n, it's 4 times. And that's how it moves you from left to right. Okay. So this here basically represents a value of x. Right? These are values of x. Once that is in place, you can build up the Riemann sum as follows. I'm going to on the side here zoom out a tiny amount. Let me make sure I can fill everything. That's our picture. So the Riemann sum will look like this. You're going to sum, or it's going to be from k equals 1. So again, that k equals 1 on the bottom, let me emphasize this. This right here, that corresponds to this. Okay. Next, take a look. In green, it goes up to n right here. I wrote on the side here. Then that's going to take you up to n up here. See that? That's why this has to match. In other words, this n matches that n, and then this one matches that one. Every piece is present for a definite reason. Okay. After that, you see, because our integrand here has an x squared, and this k times 1 over n are the values of x essentially, you can rewrite here as k times 1 over n squared. That represents the value of the function, but then you also have to multiply by the width. So in other words, you have to multiply by 1 over n, the way you see it. So let me show you this in a somewhat more dramatic fashion. For example, like this right here, this. That would be equal to the value of the function, roughly speaking, okay? And this is the base of the rectangle. So the base of the rectangle is 1 over n. And this quantity, that would be equal to, say, 2 times 1 over n, and then the whole thing would be squared. You see that? So in general, it will look like this. Take a look, because you would have to do this for infinitely many rectangles, not just for one rectangle. So this would look like this. You would do now times 1 over n. So this is like, let me write it in English. Value of function, and the 1 over n, what this represents is rectangle base. What I mean is the width, okay? Now at this point, this is a lot of just algebraic manipulation. So let me do that. Take a look. I'm gonna first take the 1 over n out of the sum, because as you can see, the sum iterates over k and not n. So the n is kind of treated like a constant in this context. You pull it out. Okay, that's one part. Then you can distribute that 2 in the exponent right here over to the k and the 1 over n individually. So it's going to give us k squared over 1, well, 1 over n squared, and this is going to be now from k equals 1 to n. I'm going to take the limit of the Riemann sum at the very end, okay, just so I don't have to write too much. So now next I'm going to say 1 over n, and again that 1 over n inside in this position can be multiplied by the 1 over n on the outside. You pull it out, so it becomes 1 over n cubed, and then the Riemann sum looks like from k equals 1 to n of k squared. So the k is the summation variable here, and now what we can do is replace the summation between 1 and n of k squared using a formula that has been developed for it. So the next stage, let me number this. This was like 1, 2, and then 3. So at stage number 4 in this process, I'm going to replace. This is going to be 1 over n cubed. And again, I'll take the limit at the very end when it's easier. And I'm going to say the following. I'm going to replace the sum of k squares as n times n plus 1, and then 2n plus 1 over 6. This is a well-known formula for the sum of squares. That's step number 5. Alright, I need to now make sure you can see everything. At this level, there's a lot of writing involved in math, so let me cancel that. And to take the limit as easily as possible, what you want to observe about the expression at step number 4 is the following, because now we're going to let n shoot off towards infinity. What that amounts to saying is that basically when n becomes a very, very large number, the width of each rectangle shrinks to 0, because the width of each rectangle, take a look, remember, is 1 over n. So if n is 1,000,000, then the width of each rectangle is 1/1,000,000th. It's super tiny. So as n goes towards positive infinity, 1 over n shrinks to 0, okay? So in other words, it's like saying you're going to end up with an infinite number of infinitesimally thin rectangles. That's the concept. So here, what I'm going to do is this. In this step, you see there's a 1 here and then there's a 1 here. Take a look right here. This is a 1 and this is a 1 in that position. When n is, for example, 1,000,000, billion, trillion, adding 1, like this one or that one to it, makes no difference. So one more time, let me stress that. In this expression, when n is 1,000,000, billion, trillion, adding 1 in either place makes no difference. It doesn't change anything. So you can drop those two ones to simplify that expression. Okay. So I'm thinking here about, doing this in the limit when n has become a huge value. So I'm going to have this now. Take a look. That the limit as n approaches positive infinity of 1 over n cubed, and then n times n plus 1, and then 2n plus 1 over 6. To simplify this, it's true that you could FOIL across the top, combine like terms. You can do all of that. It's all true. But I'm going to do it to save some time as 1 over n cubed. Just drop the constants after the n, so it becomes n, and then 2n over 6. Some people ask sometimes, why do you leave that 2 there? Well, think about it, because if you put a billion in, that's going to be 2 times billion. You see that? That doubles the billion. That's important. Whereas this 1, if you put a billion in there, it's going to be 2 billion plus 1. The 1 is not important because you're adding it. You're not multiplying. So for that reason, now I can simplify this expression as follows. The limit as n goes towards positive infinity. Cancel what you can. So on the top, what you have is n times 2n, which is 2n cubed. So I'm not going to skip that step. I'm going to have 2n cubed over 6. Cancel off the n cubes. So this one and this one. And now we have the limit as n approaches positive infinity, just to get the idea across, of 2/6, which is 1/3, like this. So basically that is equal to just 1/3, right? It's a constant at this point. And in other words, this is the value of the integral found using a Riemann sum instead. Alright, so that is it for B. Thank you so much for watching. Please give a like and subscribe. I'll see you in another mathematical adventure. There are infinitely many of them.